So, taking a look at number 2 from Unit 1, Exam 1 from 2014. It's about Newman projections. So it says, draw the exact conformation of the molecule below as shown in a Newman projection looking down from C2 to C3. So first let's draw it. Okay, so here's the Newman projection, or not the Newman projection yet, but here's this, they call it the sawhorse model. And we want it to look down from C2 to C3. So I would want to put my eyeball going this way, looking down that way. So I always start off with the Newman projection, right? Draw a circle. And now in this case, if you looked at it, there's something in the middle. C2 is right here. Now if you're looking your eyeball down here, what's up and to the left is the H. You see how that's kind of up and to the left over here? Right? So that would be the H. Up and to the right is going to be the F, and down is that methyl. Now if you keep going back, you notice this H and this chlorine are what to each other? They're eclipsed actually.
Well, how would they not be eclipsed?
As I have it drawn here, they're always eclipsed. But what we're going to do though, is we're going to rotate about this C2-C3 bond. So as I have it drawn right now, it's eclipsed. So the first question was to ask you just to draw it exactly as it's shown. Right? And then we'll worry about rotating in a second. Right? So everybody see how the chlorine and the H are both kind of up and to the left here, right, from this angle? So they'd be eclipsed. So this would be the chlorine there. This would be the other H, because the H and the F are kind of eclipsed. And then this ethyl is going back. Right? It's also this ethyl and this methyl are both right in the same plane. Okay? So another way to think about it right now, more terms you know now that you didn't know then, right? These two ethyls are syn to each other, right? Or cis, right? The chlorine and the H are syn to each other, right? These two H's are trans to each other, right? So there's things that are anti to each other, right? So maybe these Newman projections are easier to see now than they were maybe before. Okay, so this is drawing it exactly as it's shown. And the next part says rotate carbon 2 counterclockwise, not clockwise, counterclockwise. So we have to look at a clock, and that means rotating to the left. So that means rotating the F, the H, and the methyl, right? Rotating carbon 2 counterclockwise 60 degrees. So how many degrees in a circle?
360.
360. Right now, if you divided 360 by 3, that would be what?
120.
120. Very good. Right, so there's 120 pieces. We're rotating 60 degrees, so that means this F is going to move from being eclipsed to being staggered, one spot over, right? So you see how we're going to rotate it 60 degrees. Yes? So what that means now, I draw my circle again. The back stuff never changed, right? The chlorine, the H, and the ethyl never moved, right? But everything else did to the left. So here's the F, here's the H, and there's the methyl. And then I ask you to do it again and again. Do a lot of rotating here. So we rotate another 60 degrees with C2. So now it's going to go from staggered back to being eclipsed again.
Well, which way is it rotated?
Counterclockwise still. Yep, so I'm still going this way. So again, the back part just stays still, right? Nothing changes. Right, so the point of this is, right, when you only want to rotate one carbon at a time, otherwise it gets too weird. So now the fluorine and the F are syn. The H, there's methyl right there. And then we want to do it one more time, why not? 60 degrees, counterclockwise. Now again, we're going back to being staggered. But again, what didn't change? Or the chlorine, the back part never changed, that's right. So there's the H, there's the F, there's the methyl. So we label these, this could be A, B, C, and D. Another part of this question is, which would have the largest dipole moment? Which is going to have the largest dipole moment?
B,
B. Good. Why B?
because the chlorine and the fluorine are.
Yeah. Eclipsed, and that they're both electron negative, so they're going to have the most electron density pulling that way. Which one's going to have the smallest dipole moment? Probably
D.
Would it be the exact opposite where the halogens are like?
D. Yeah, get the smallest dipole moment. Halogens farthest away from each other, right? Because they'd be pulling against each other in opposite directions. So this is probably the smallest.
So this dipole moment's like directly translated to energy too, right? So
Some level of dipole moment is somewhat directly related to energy, right? Dipole means it has like either one area or an area of the molecule is kind of delta minus or delta plus.
what would B be the most energetic?
B would probably be the most unstable for a lot of reasons, right? The eclipsing stuff, and also having, but I mean, so it's kind of the same answer, right? Having the electrons near each other is bad, or high in energy, right? They don't want to be bumping into each other as well.
Is there any point where carbon, like if you had like an octanol on one, or like an octane, and you had like Cl and F, would the octane ever overrule that, or is it always the ions that are?
The electronegative things usually make a bigger difference. I mean, there's probably a point where a big carbon chain would start messing things up just because it's non-polar, but this is about polarity mostly.
Okay.
Good. So taking a look at number 6 from exam 1 from, actually this is this year, sorry, last year, this year. So for this one, it's asking about acidity, and it's comparing these two molecules. Right, so you look at this and say, okay, first, I mean, obviously numbering carbons is, there's nothing wrong with that, because what's different here is, so you're asking about acidity, so we can assume the most polar bond to hydrogen is what we're talking about, and that both these cases would be an OH bond. And it looks like there's 2 carbons in between the alcohol and something else, right? So that's not, so the distance away is the same. So the only real difference here is what? Chlorine versus iodine, right? So we look at the periodic table and say chlorine and iodine. What's their relationship to each other in the periodic table? They're halogens, so in the same period, right? And which one? And what do we know? So iodine's bigger, chlorine's smaller, right? What do we know about their electronegativity?
Chlorine's a lot more electronegative.
Chlorine's more electronegative, so it's going to more likely pull away electron density, right? So chlorine's more likely to pull this way than iodine, right? So chlorine's more likely to make this bond more polar, more reactive. So that makes this a more reactive acid, because chlorine's more electronegative. It has nothing to do with size. Size has nothing to do with this. It's about electronegativity in this case. So in another case was, what's the difference between, say, something like this versus this? Right. So again, we're focused on the H. So the biggest difference here is, right, the hybridization state. So when we talk about this being an acid, right, for something to be reactive in any case, either has to have reactive materials, reactive bonds, or form a stable product. Now in both of these cases, what do you guys know about CH bonds in general?
They're pretty stable.
They're really stable, they're not reactive. So both of these bonds are not reactive. That's a fact. So it must be the case that one of them must form stable products though, right? Because you can have really stable bonds, but the product you form could also be really stable, right? So CH bonds, no matter what the hybridization state is, right? These are not reactive. So let's look at the conjugate bases of these. What do they look like? So they would look like having a negative charge there, or having a negative charge here. Now there's a difference. This is actually stable, relatively speaking, whereas this is unstable. The question is why? Where are these lone pairs? What molecular orbital are these lone pairs in?
SP2.
Nope, sp3. These lone pairs are in an sp3 orbital, right? They're always in an sp3, right? There's not a carbocation, this is a carbanion. So sp3 means they're farther away from the nucleus, right? And the nucleus has what charge? And so it'd be better for it to be closer. So one way it could be closer is being in an sp orbital, right? This is an sp orbital. The negative charge is in an sp orbital. Closer to the nucleus, that makes it more stable. So in this case, the conjugate base of an sp hybridized CH, right, is much more stable.
So it's going to be more reactive?
So it's going to be a more reactive acid, right? This is because the product, the conjugate base is stable. That's why. All right, doing quiz 2 from this year. Number 3 has to do with an alpha cleavage.
Yeah.
So we have a OH, alcohol. So the first step, it hits the electron beam. So the first thing that happens is one of these electrons gets shot out, right? Knocks the tooth out, knocks out one electron. So we make the radical cation, right? So we lost an electron, so now there's a plus charge there. One of those electrons is unpaired. And so the alpha cleavage, the way that works is if you say alpha, beta, and then gamma, whatever's bonded to your function group is considered the alpha carbon. And that's considered the alpha carbon, so we're going to do an alpha cleavage. So we're actually going to break the bond between the alpha and the beta. So I'm going to draw the electrons in, right? Because how many electrons are in a bond? 2. Right? So we're going to break that bond. And we're going to use fish hooks. We're going to use radical arrows. So just because now we're going to move one electron at a time. Because we're doing radical chemistry, right? We just knocked one electron out. Oops. Right? Right? So you see one electron, the one fish hook kind of arrow, not the double-headed arrow, just the one. So we're moving one electron at a time. So to do that, let's, whoops, went too far. Put my electrons back in. So let's see. I'm going to break this and have the electron, right? The unpaired electron, they're going to form a new pi bond between the oxygen and the alpha carbon. And this other electron is going to end up on the beta carbon. So we're breaking the bond between the alpha and the beta carbon. So the beta carbon now, right, got one electron, right? And now there's a new pi bond between the alpha, right, and the beta or alpha and the oxygen, alpha carbon and the oxygen. And where's the plus charge at still? Still on the oxygen, that's right. Alright, so this is the two pieces of an alpha cleavage. Which piece do you see in the mass spec? The radical or the cation? Only the cation, right? Mass spec, you only detect the actual plus charge thing. This is the only mass you would see. You don't see the radical piece. Right? Now, if we could, we'd rather make radicals that are, what? More stable, right? Just like we'd rather make more carbocations that are more stable. Right? So what kind of carbocation, what's the most stable kind of carbocation? We'd want to have tertiary, right? Or lone pair resonance or pi bond resonance, all those things we did before. Right? So we'd rather have more stable fragments if we can. So a question about UV vis and how conjugation affects pi to pi star in the wavelength. Right? So the more conjugation you have, do you think it's going to be easier or harder to go from pi to excite to a pi star state? If you have an electron, the more conjugation you have, it's going to make it easier, take less energy, right? The energy gap here is going to be less. So is that going to be longer or shorter wavelengths? longer wavelengths, right? Long wavelengths, low energy, right? A long wavelength means lower energy. A short wavelength means higher energy, right? Visible light is a longer wavelength than ultraviolet light, right? So the more conjugation you have, right, the smaller the energy gap, the longer the wavelength. Now, one way we could apply that, right, and it depends. Sometimes this, right, in this case, there'd be more electrons in this pi system. So you expect, right, it would take less energy to go from pi to pi star. Versus, let's say you had NH3 plus, right? Is there a lone pair in the nitrogen that it can share with this pi system? No, it doesn't have that lone pair anymore, right? Because now it's bonded to hydrogen. Whereas this oxygen has more lone pairs to share with the pi system, right? So this would essentially means there's like more conjugations, more electrons in the pi system. So it would make sense that this would take a longer wavelength, lower energy to go from pi to pi star. Whereas this one is going to take a shorter wavelength, it's going to take more energy because this nitrogen is not helping donate electrons into the pi system. So the more electrons in the pi system, the more conjugation, right, usually means it takes less energy and a longer wavelength to go from pi to pi star. Because that's what's happening in ultraviolet light. You're not breaking bonds fully, you're exciting a pi electron, right, an electron in a p orbital, in a pi bond, up from pi to pi star. And then what you see, the color you see is what's coming back when it comes back down. That's what you see, the fluorescence, or the giving off of energy. All right, number 6 on exam 2 from this year. This is you're given an IR and you ask which molecule will match this. So a lot of times in IR you gotta look at not only what's there but what's not there to figure out what you have. And so it's pretty clear in this one you do not have a broad OH. Hopefully everybody would see that with this. So that immediately eliminates 2 things, right? The 2 things with OHs, right? So these are not possible, right? If you don't see an OH, it can't be those 2 things. Now, the next thing, right, you look at these differences. Well, this has 2 aldehydes. This has an aldehyde, but it also has a nitrile. Well, where do nitriles have stretches at? 2200. Right? And if I don't see anything at 2200, this is also eliminated. Right? So what I usually do is I look for stuff that's not there before I worry about what's there and try to match things, right? What's not there? Right? If there is no OH, then this can't be the molecule. It doesn't matter that there's an aldehyde, right? If there's no OH, it can't be these 2 things. If there's no nitrile, it can't be this. You must have all the functional group stretches present for that to be the molecule. And essentially at this point, that just leaves this. Now we can go back and justify why it's that. And we can say, oh, it's an aldehyde. Well, aldehyde has this Fermi doublet, right, at 2820 and 2750. Right, it has 2 stretches there. An aldehyde would have 2 C double bond O stretches, right? Because there's 2 different aldehydes. We'd see a stretch at, 1700 or 1680 or 1695, right? This is the only one that matches up, right? You got to recognize there is no OH. That was the big key here. There's no big broad OH. It can't be these 2 things.
Is OH always broad?
Yes. More often than not, OH is broad. As far as you guys can care or want to know. Yes.
There's no CN.
And there's no CN stretch, right? There's nothing at 2200. Nothing strong, right? You expect to see a big broad peak, right? Or big, not broad, but big strong peak, right? Going down a long ways.
Can we get one of those papers?
Absolutely. I give you all the papers.